All right, welcome everyone. So today we are starting chapter 5 of Wackerly, talking about multivariate distributions. So looking at probability distributions of 2 or more variables at the same time. Based on what we're talking about in class today, I recommend trying those 3 problems on homework 7 after class today. And as a reminder, we also have our review session on Thursday for the second midterm. So please work on the practice exam problems that are up on Canvas so that you know what questions you want to ask about on Thursday. All right, so let's start off with a review question that will then become our first example. So let's suppose that a committee has 3 Republicans, 2 Democrats, and 1 independent on the committee. And they want to choose 2 people uniformly at random for a subcommittee. So choosing 2 people, and each person on the committee is equally likely to be chosen. Let's let X be a random variable that represents the number of Republicans on the subcommittee, and Y be another random variable that represents the number of Democrats on the subcommittee. Find the probability that X equals 2 and Y equals 0. Okay.
Is it 2 tenths?
Let me see what I got. 3/15. So 1/5. Yes. So we could do this in either of 2 ways. One way would be to use counting methods from way back in chapter 2. We have the number of ways to choose 2 Republicans is 3 choose 2, and the total number of ways to choose 2 people would be 6 choose 2. So we get 3/15, 2 tenths, 1/5. The other way would be to do a conditional probability tree. So the probability that the first person we pick as a Republican is 3/6, and then multiply that by the probability that the second person is a Republican, given that the first was a Republican, which is 2/5. Questions about this? All right, so we could do this for all combinations of X and Y, right? X being from 0 to 2 and Y being from 0 to 2. And we could write this as a table. So when we do this, this is the joint probability function of X and Y. So we can write this as lowercase p of little x and y, representing the big P probability that our random variable capital X equals some number little x, and our random variable capital Y equals some number little y. All right, so some important facts about multivariate distributions for discrete random variables. First of all, for any values X and Y, what can we say about little p of X comma Y? What must be true about the probability that X is little x and Y is little y? It has to be greater than or equal to 0. Yeah. similarly, what can we say about the sum of the probabilities in this joint distribution over all possible values of x and y? Kyle. It should equal 1 because these are probabilities and we're summing over all possible values of x and y. So these facts are just like what we saw in the one variable discrete case, just now we're working with two variables. All right. Similarly, we can think about a multivariate version of the distribution function. So the probability that x is less than or equal to x and y is less than or equal to y, which we can write as capital F of x comma y. So, for example, in our committee example, what is big F of 1, 1? Okay.
6/15.
So 6/15 is the probability that x equals 1 and y equals 1. But for big F, we want the probability that x is less than or equal to 1 and y is less than or equal to 1. So for that, we want this whole region of our probability table. So 6/15 plus 3/15 plus 2/15 plus 0. All right. So this gives us a way to get to an idea of joint probability density functions for continuous random variables. So if x and y are continuous random variables, and we can find some non-negative function little f, so that when we take the integral of that, as t goes from -∞ to y, little y, and s goes from -∞ to little x, where that is equal to our joint distribution function big F of little x comma little y. Then we can say that little f is the joint probability density function. All right, so the way to visualize this joint density function is to think of it as being a surface that has a height over the xy plane. And then the volume under that density function on a region is the double integral of the density function on that region. That is going to give us the probability that x and y are in that region. So previously, when we've been working with one continuous random variable, we would just take the integral of the density function, So we'd find the area under the curve, and that would be the probability that y was in that region. Here we're doing the same thing, but with a double integral. Kyle. Good question. It's going to stay functionally the same. It's going to be the double integral of whatever quantity you're finding the expected value of times the density function. All right. So to take an example of this, let's suppose that a radioactive particle is located uniformly at random in a 1x1 square, and we'll let x and y be the coordinates of the particle on the x and y axes. So if it's located uniformly at random, that means that our density function has constant height. So our density function equals 1 when x is between 0 and 1 and y is between 0 and 1, and it equals 0 everywhere else. So you can visualize this as little f, our probability density surface, is a flat plane at a height of 1 sitting over the unit square. And there's an image of what that might look like. So let's find the probability that the particle will be in this blue rectangle. So try writing that as an integral. All right, so we have a double integral of the density function, which was 1. We have dx dy for our differentials. And then our bounds of integration are the bounds of the region we're interested in. So x is going from 0.2 to 0.4, and y is going from 0 to 0.4.
Hi,
and in this, oh, yes.
Is it possible if I do the other way around?
Good question. So yeah, in this example, we could do the integral in either the dx dy or the dy dx order. We'll see an example in a little bit where it's easier to do it one way rather than the other. But the thing to pay attention to is to make sure that your bounds of integration match up with whichever variable you're working on. So dx, x should go from 0.2 to 0.4. So here we have dx as the inner differential. So our inner integral should go from 0.2 to 0.4. Other questions about this example? All right, so let's try a more complicated example. Suppose that x is the number of gallons of gas in my car's tank on Monday, and y is the number of gallons of gas I use during the work week. And I never have time to fill up on gas during the work week, so y is always less than or equal to x, because I can't use more gas than I start the week with. And let's suppose our density function is 3 over 1,000 times x for 0 less than or equal to y, less than or equal to x, less than or equal to 10. And the density function equals 0 elsewhere. So one way to picture this would be to just visualize the xy plane and sketch the region where the density function is positive. So the region y is greater than 0, so positive y-axis, y is less than x. So draw the line y equals x, and then we're going to be below that. And x is less than or equal to 10. So we're in this triangle drawn here. So the density function is some surface lying over that triangle. So here's how you might visualize that. In 3 dimensions, it would be this triangular prism, so like a pyramid lying on its side, where the base of the prism is this triangle that we drew in the xy plane. All right, so we want to find the probability that I start the week with less than 5 gallons and use more than 2 gallons. So for this problem, we're looking for the probability of being in this shaded region on the left-hand graph. So x is less than 5 and y is more than 2. So in other words, that would be the volume underneath the density surface within this shaded triangle. All right. So the first thing we need to do for this problem is to choose the bounds of integration, right? Because we know what's going to go in the integral. That's going to be the density function. So that's already given to us. So the hard part here is picking what the bounds of integration are going to be. So here we've got this image of our region, and we want to think about drawing a sample rectangle in this region. So for example, we could draw a sample vertical rectangle, this red line, that is starting at y equals 2 and going up to the line y equals x. I want to come back to that. So if we have vertical rectangles, then our order of integration is going to be dy dx. So the idea here is that first we'll do our integral along the red line, and then we'll change which rectangle we're looking at and sort of slide this example rectangle horizontally along the shaded region. So that would give us dy dx. The inner bounds of our limits of integration then are going to be the bottom and top ends of the rectangle. So our inner integral would be dy. Y is going from 2 up to x. And our outer bounds would be the position of the first and last rectangle. So the first rectangle would be at x equals 2, and our last rectangle would be at x equals 5. So our outer integral goes from 2 to 5. Questions about that part? All right, now let's come back to these other examples. Let's suppose that instead of the probability of being y greater than 2 and x less than 5, we instead wanted this blue region. So we don't care about x, but we want y to be less than 6. In this case, it's much easier to use horizontal rectangles than to use vertical rectangles. The reason for that is that look at this horizontal rectangle. That works perfectly fine. But if we used vertical rectangles, that would be annoying because our example rectangles don't all end on the same line. So if we used vertical rectangles in this example, our inner integral would have to change upper bounds from being equal to y equals to x or being y equal to 6. So you'd need to do 2 integrals and add them together. So in some cases, like our example on the left here, you can do your integrals in either order. Doesn't matter. But in this example on the right, then it really is easier to pick one type of rectangle over the other. So one of the orders of integration is going to be easier. Questions about this? All right. So let's go ahead and try vertical rectangles here. So we said that our inner bounds of integration should be the top and bottom edges of the rectangle. So from 2 up to y equals x. And our outer bounds of integration should be the position of the first and last rectangle. So x equal to 2 up to x equal to 5. So an important point here is that here y is going from 2 up to x. The inner bounds of integration can depend on the other variable, the one that's not the one in the differential for that integral. But the outer bounds of integration need to be between constants. So the outer bounds can't depend on either variable. All right. So to solve this, it's going to be a similar process to what we did in chapter 4. We'll start by just doing the inner integral. And because we're integrating with respect to y here, remember we're treating x as a constant. So we can pull the 3 over 1,000 times x all outside of the integral. And then we just have the integral of 1 dy from 2 up to x. So that becomes antiderivative of y, which we're evaluating at x and 2. So we have 3 over 1,000 times x, which that was all our constant factor, times the quantity x minus 2. So we get 3 over 1,000 times x squared minus 2x. That's the result from our inner integral. All right, so we've solved this part in blue. We can now replace that with what we found for our inner integral. And now we can do the outer integral. So antiderivative of x squared is 1/3 x cubed. Antiderivative of negative 2x is negative x squared. And we're evaluating at 2 and 5. So we end up with 0.054 is the probability that I start the week with less than 5 gallons and use more than 2 gallons. Questions about this? Folks online, any questions? All right. All right, so let's look at another example. A company offers a basic life insurance policy and a supplemental life insurance policy. To buy the supplemental policy, you must first buy the basic. And let's let X be the proportion of customers who buy the basic policy, and Y be the proportion who buy the supplemental policy. So 0 is less than Y, is less than X, is less than 1. And let's suppose our density function is little f of xy equals 2 times the quantity, x plus y, on the region where the density is positive. So on this region defined by the inequality we looked at earlier. Try writing an integral for the probability that x, proportion who buy the basic policy, is less than 0.5, and y, the proportion who buy the supplemental policy, is less than 0.25. So I always recommend starting with a sketch of the XY plane and the region that we're interested in. So here, the total region where the density is positive is this triangle in the lower right-hand corner of the unit square. And then we're interested in the probability of being in this blue region. So x is less than 0.5 and y is less than 0.25. So for this region, would you rather use vertical rectangles or horizontal rectangles? Yeah, horizontal rectangles. Why?
You have 2 opportunities for vertical.
Yeah, if we had vertical rectangles, we'd need to go up to different lines depending on whether x was less than 0.25 or greater than 0.25. So we need to do 2 separate versions of the integral. So if we use horizontal rectangles here, that's going to be order of integration dx dy, because first we're integrating along the length of the rectangle, and then we're moving the rectangles up and down. So our integrand is our density function, 2 times the quantity x plus y. Our bounds of integration, so for x, we look at the endpoints of our example rectangle. So the left hand or lower endpoint, x is equal to y, because this is the line y equals x. And then the larger endpoint is x equal to 0.5. And then our outer integral, the lowest possible rectangle we could draw would be at y equals 0. And the highest rectangle we could draw would be at y equal to 0.25. So we end up with our outer integral having constant bounds, which is what we want in order for our answer to be a probability that's actually a number. Questions about this? Kyle?
How did we get the big triangle?
This big triangle in the lower right-hand corner?
Yeah.
That is coming from what we were told on the restrictions on x and y, that to buy the supplemental insurance, you first had to buy the basic. So y must be less than x.
Yeah.
And you can check that our integral of our density function on this region should be 1, just like we had for a single continuous random variable.
Doctor,
Yes.
do we always refer to the graph of y equals to x?
So this diagonal line here?
Yep.
No, like there will be problems where we're looking at just a rectangle, or where we have the restriction that y is less than 2x or greater than x over 2. So that's going to vary, but I would say that a lot of problems end up using some restriction on y is less than x or y is greater than x, because it makes for problems that have some interesting shapes to them without being too computationally messy.
So if they didn't mention the restriction, we will just put it as y equals to x.
So the problem should always give you something about the restriction, either in a form of an inequality like this, or in something in words that you can interpret to get an inequality like this. So you could get this inequality if all the problem gave you was this first bullet point, that we're interested in the proportions, so it's going to be between 0 and 1, and to buy the supplemental you must first buy the basic. That means that y must be less than x. So you could figure it out from the text without being given this inequality, but somehow the problem needs to communicate what the valid region for the density function is, where it's positive.
Okay.
And like, for example, in our first problem here, the particle was located uniformly at random in this 1 by 1 square. So here, the only restrictions were that x is between 0 and 1 and y is between 0 and 1. So here we didn't have a restriction of how x had to relate to y. We just had restrictions on the value of x, and separately a restriction on the value of y. Does that answer your question?
Yep.
Cool.
Thank you.
Other questions about our Other questions about this example? All right. Give this one a try. So the lifespans in months of two components of a machine have joint density function 6 over 125,000 times the quantity 50 minus x minus y. For 0 less than x, less than 50 minus y, less than 50. So try writing an integral for the probability that component y is still working 20 months from now, and component x is not. So I recommend starting by sketching the overall region where the density function is positive. So sketch the region where 0 is less than x, is less than 50 minus y, is less than 50. So that's going to look like this. So we have that x must be greater than 0. So that gives us this left-hand line on this triangle that x has to be positive. And we have that x is less than 50 minus y. So to get that, draw the line x equals 50 minus y, or equivalently y equals 50 minus x if you just solve that for y. And then test a point on either side in order to pick the side where x is less than 50 minus y to make sure you've got the correct direction. Everybody okay with this first part, drawing this overall region where the density function is positive?
Yep.
All right. So then sketch in the region where we have x and y in the region we're interested in to compute the probability. So we want component y to be still working 20 months from now, and component x is not. So we want the probability that x is less than 20 and y is greater than 20. So that region looks like this. So do we want vertical or horizontal rectangles here? Kind of? Yeah, how come? Yeah, if we drew them horizontally, we'd have to go up to x equals 20 for the lower rectangles and up to x equals 50 minus y for the upper rectangles. So let's go ahead and use vertical rectangles here. So now using that fact, try to write the integral. All right. So because we have vertical rectangles, we want the order of integration to be dy dx. We have our density function that we were given. And then the bounds on y are from 20 up to 50 minus x. And the bounds on x are from 0 up to 20. Are there questions about this? Folks online, any questions? All right. Give this one a try. So stock prices of two companies have joint density function k times x for x between 0 and 1 and y between x and x plus 1. Find k to make this a valid probability density function. So what's our overall strategy for this one going to be?
You know, it must equal 1, right?
Yeah, the double integral needs to equal 1. So I recommend starting by sketching the region of integration, just like we did in that last problem. All right, so here's our region. X is between 0 and 1, and y is between the line y equals x and the line y equals x plus 1. So we get this sort of diagonal strip of a region. So based on this, we're going to want to use vertical rectangles so that we can consistently go from the line y equals x up to the line y equals x plus 1 rather than changing our endpoints of our rectangles. So the integral that we want to be setting up is the integral of kx dy dx, because we have vertical rectangles, from y equals x to x plus 1, and then from x equals 0 up to x equals 1. All right, so when we evaluate this, focus on our inner integral. Here we're integrating with respect to y. So both k and x are constants as far as this integral cares. So we have kx is our constant times the integral of dy is y. So we have kx times y evaluated at x and x plus 1. So we have x plus 1 minus x, the x's cancel, so we're left with just kx as the result of our inner integral. So then for our outer integral, now we have the integral of k times x as x goes from 0 to 1. So our antiderivative is k times 1/2 x squared, plugging in 0 and 1. We get k times 1/2 minus 0. So the outer integral is k over 2. And remember that our goal was for this whole thing, this double integral, to equal 1. So now we have that k over 2 must equal 1, so k is equal to 2. Questions about this? All right, thank you for your attention. I will see you on Thursday for our review session.
Thank you, Doctor.
You're welcome.